things which of no interest actually, no physical interest. There are some small things we can do. In bigger dimensions, it is always true that mu is given by this. So here we see there is a sort of linearity assumed only on orthogonal things. But still all those things put together and you get that it is always in a sense a linear map. Okay. And the proof is not easy, and all the difficulty is in dimension h equal to 3. So you can prove it for dimension h equal to 3, then you can get a general one. But h equal to 3 is the hard part. And you can see a proof in the book of Sarati, the Introduction to Stochastic Calculus, Introduction to Quantum Stochastic Calculus. So this gives us the third ingredient, rho. Okay. So instead of mu, I will be writing rho because they are described by this kind of density matrices. Every measure would be given by a rho. Okay, by a density matrix. Okay. Now, what is the next step? So next step in classical probability. So if you have omega f mu is the probability space you start with, but that is not what you work with generally. What you work with are the random variables. Okay. So this is what we call probability space. But then you have random variables. So what are they? They are functions from omega to r which are measurable with respect to this. You put Borel sigma field on r and you have measurable functions from omega to r with respect to this. So this x actually has nothing to do with mu. It is only talks about omega and f. So it is the distribution would depend upon mu, but sometimes we change the mu. That's why I am saying this x, the measurability depends only upon this omega and f. Okay. Here the simplest ones are the indicator functions, right? A belonging to F. So you have this sigma field omega with all subsets, okay, measurable subsets. For any subset A, I can talk about the indicator function, which is the function which is 1 on A and 0 on the orthogonal component. It's always measurable. Okay? So correct. The A of omega equal to 1 if omega belongs to A and 0 otherwise. So indicator functions. Then you have simple functions. Which are really linear combinations of such things. Okay. CIs have some real numbers. And then general functions are basically limits of such things. Right? So you start, the simplest thing are the indicator functions. And then there are linear combinations which we call as simple functions, and then there are limits of the general measurable functions. And what do? You also assign, once you have a random variable like this, then we get a probability distribution on the real line. So that is under mu, the probability that x belongs to b. Okay, so here is omega. You have a function from x to the real line. If I take any set b here, probability that x belongs to b is just defined as mu of x inverse b. Right? Look at all those omegas which are mapped to b. So that is a measurable set here. Take mu of that. So that is the probability that x belongs to b. Okay. So in particular, say for this indicator functions, so indicator of A, probability that that indicator function that takes the value 1 is mu of A, and the probability that the indicator function takes the value 0 is 1 minus mu of A. Okay. So that is the simplest case, and from there we go to the general thing. For any random variable x, you define mu like this. So you sort of induce the measure to this. So the same things we do here. Okay. So my space now is just this, right? H, pH and O. So I have chosen and fixed a density matrix O. So now if I go along this line, so indicator functions. What are the things analogous to indicator functions here? Projections, right? So you take any projection, so that you think of as an indicator function. So if say P is a projection, think of it as a random variable now, right? It is like an indicator function. So indicator function. So the probability of that P occurring, okay, so that is under mu. Now I have rho actually. Stress rho P. This is what we said. We have assigned probabilities to events, okay, which are projections. So probability that this projection occurs, okay, is trace rho P. That is something between 0 and 1. Okay. Probability that P equal to 0, that is same as the P per pair occurring, okay, and that is 1 minus this, which is trace rho P per.
Equal to 1, you mean that is identity of
No.
Event.
This is a language of probabilities. So P, right? P equal to 1 doesn't mean that P is equal to identically equal to 1. Yeah. So see the interpretation is
always coming from classical.
It's a language of classical probabilities. So you just understand that we assign the probability trace rho P for P. Okay. So see, when you have a random variable, it may take different values. Like when you throw a die, okay, so it can take any value from 1 to 6. Okay. So suppose I take X as the outcome of your throw. Then we write like this, probability X equal to 2 is 1 by 6. Okay? It's not that X is equal to 2. X is a function, 2 is a number, right? But the chance that you will see 2 as the outcome, that is 1 by 6. That is the way.
So P equal to 1 here is a notation for P occurs.
Yeah, exactly. So notation that P occurs. It is. It's not mathematically P equal to 1. No, it is not the case. Okay. So it's a more language rather. Okay. All it is saying is that we are assigning mu of P as trace rho P. That's all. What we had before. So now, if I have in P of X. Suppose I take some orthogonal projections, okay? Suppose P1, P2, Pn are mutually orthogonal projections. Okay, so that means Pi is perpendicular to Pj for I not equal to j, and I look at this x equal to say summation Aj Pj, j from 1 to n. Aj belongs to R. So this is like your simple function. That means you wake up omega, say, let me take their sum to be equal to identity. So here, say in omega, in the classical case, suppose you break it up into disjoint sets, A1, A2, An. Okay? Disjoint sets, union is omega, and then you can have a random variable which takes the value A1 at A1, A2 here like this. So x will be summation AI indicator of A equal to 1. So this is a simple function, okay, which takes the value A1 in the set A1, A2 here like this, An here. So this any simple function would do it like this.
Do you need the exhaustivity or you need that here?
Not quite. Means it is the same thing here.
Okay.
If it is not there, I can always put
Always put the complement as
you
zero.
can put 0
Now
times
just without assuming something.
Yeah, you can put 0 times the orthogonal. It's no problem. So if you like write like this, okay. So this is a simple function. In A1 it takes the value A1. At A2 it takes the value A2 like this. Then what we have is the probability that x equal to the takes the value AI is mu of AI. Okay. So x takes, these are the possible values of x. A1, A2, this A1, maybe I should call them CIs. Because that way it's, I don't have to say capital and small, right? So these are the CIs, are the values of the random variable. It takes